Okay, thanks. So today I will discuss decision making under uncertainty, and the presentation will start with a short overview of our research vision in my research group, and then I will go into a little bit more details about a couple of robotic applications, and then also discuss the methods that we are using in planning and reinforcement learning, and hopefully also connect it to some of the applications that people here have. So our research vision is related to the current trends in AI and machine learning and robot autonomy. So if you look at this, I hope you can see. So here's, for example, a robot climbing the stairs. So the idea here is that the robot would become very autonomous in its behavior. And for example, we have used this robot on construction sites to collect data. So that's kind of like one first step. Another thing is that robots need to work together with humans. And the third thing is that robots need to work in unstructured environments. And in order to do that, you need machine learning and to process limited information, sensor uncertainty, and you have to cope with uncertain behavior of other machines and the humans. So this is kind of like the high level idea. And we develop methods for planning under uncertainty and reinforcement learning and do also manipulation and mobile machines. So at the moment we are focusing a lot on reinforcement learning. So I guess this was already discussed a little bit in the previous presentations. Now I will give you a concrete example what we have been doing. So here's a pile of scrap iron and waste and plastic waste. And then there's a robot grasping a plastic part here. And in these situations, you don't really see what's really inside this pile. So it's a very hard problem to actually disentangle the object from there. So what we want to do is we want to find a path planning method that can handle unknown objects in an unseen environment. So we don't know anything about the environment in advance. And in order to solve this problem, we create a probability map. So we try to pull things out, so this plastic out, and then we notice that it can't go anywhere. We have a compliant robot arm, and then we record this into a database and then create a probability map for that. And then we try to find the most probable path that does not have any collisions, and we iteratively repeat this. And the method is general, so we're also now trying it out on a mobile robot, so it's not limited to disentangling waste. And so we tried this out on a real robot in several different situations. And here's my favorite example. We have a bunny, so this is a toy bunny, not a real bunny, inside the box, and then we try to squeeze it out. But actually you can only pull it out if you go from this side, so you have to try out many different things before you succeed here. And I hope the robot succeeds. Yes. Yeah, I was already a little bit worried. Okay, so yeah, so this was just one example. So all of our work somehow involves this very general cycle of a robot performs an action or a heavy machine or whatever, and then it changes somehow. The world changes, and then you get an observation back to the robot. And you can use many different methods for solving this kind of problems. So for example, we use reinforcement learning, and then we use planning with known models, reinforcement learning with unknown models, and then you can use also optimal control. And this is another example of our work. So here we use planning, and the idea is that the robot is not sure what is inside these boxes. So there's some uncertainty in the, for example, of the physics of the boxes, and in this case we just have some objects inside them. And then we have a human who can tell the robot more information if the robot asks. But for this, the robot needs to make very complex plans so that it knows what is the most efficient way of actually stacking the boxes but at the same time not asking the human all the time questions, but doing it in an intelligent way. And in the end, the robot then learns to make. The video is not playing for some reason. Okay, yeah. Okay, yeah, let's skip the video. Anyway, the robot would be stacking the boxes in the video and then asking the human questions, and the human can choose from an UI then what is the actual correct answer. Okay, and so this work was based on planning methods. So we developed planning methods. For example, one specific method that we have been developing lately is the Monte Carlo tree search. And okay, this goes a little bit into the technicalities, but the idea is that you have a kind of like a planning problem. You have either a simulator or a model that you can use, and then you try out different actions, and depending on the action outcome, you then choose different actions again, and you build this kind of like tree in a very optimistic way. But this approach is nice. You can combine it with heuristics, so you can give prior information about your problem. For example, if let's say if you do like this planning problem in kind of like high-level decision making, for example, this stacking boxes, you can tell some simple rules to the system to make the planning even more efficient, and it's easy to incorporate. And Monte Carlo tree search has been used, for example, in many robotics tasks and also beating the world champion in Go. And the actual details of our contribution are related to the actual algorithm which uses the average operator to average over rewards or values, or another common way is to just the maximum. And the average operator results in this flat tree. So this is not a real tree, you can see that as an illustration of the search tree. And another possibility is that the tree is very deep, so it plans very far into the future but considers only very few choices. So in our opinion, this is a bad way of doing it, and then we developed a new way of doing it and prove that it converges to the optimal solution. And then we get these kind of like very nice looking trees and improved performance. Okay, now let's get to the final part of the presentation. So there was a discussion from Ville about what reinforcement learning is. So basically, reinforcement learning is a very general approach that you can use to learn, for example, control or also high-level decision making. And it is especially useful in situations where you, for example, don't have a full physics model of the environment. So this could be, for example, with hydraulics machines, which are hard to model, or, for example, in earth moving, you might have different kind of like earth. This is also a hard modeling problem if you want to have like an exact physical model, or if you drill like some rock or many natural environments are hard to model exactly. And kind of one of the main problems with reinforcement learning is that you need a lot of data. So if you put the reinforcement learning on kind of like a mobile machine, for example, you need to run it for a very long time to actually learn complex behavior. And our idea now here is that we will do curriculum learning in reinforcement learning in a specific way. So curriculum learning is known by most people. So human babies do it, so they start with simple tasks and then build their skills by going into more harder tasks. But in our case, we do it in the way that we optimize the speed of learning and incrementally make the task harder. So here we have an example. For example, here's a robot arm catching a ball. It's this red dot here. It's coming towards us, so this red line shows that it's okay, it's coming towards our face, but we need to catch it with this robot arm. And then we can control in some way how close the ball passes the robot arm cup here. And of course, if it's closer to the cup, then it's easier to catch the ball. And the algorithm then automatically determines the distribution over ball positions and slowly transitions to the final hard task so that the robot arm can catch the ball in many different positions. And this is applicable to many different situations in control of machines. Here you can see some results. So here you can see kind of like a default reinforcement learning algorithm. It's controlling four-legged ant. This is actually the same ant that was it Arno or Juha had in their presentations, but this is a simulation of that one. And basically you are controlling leg locomotion, so all the legs of the ant, and you're trying to go through this gate and arrive on the other side. And our approach works the best in this case, so it learns pretty quickly to go through the gate and control the legs of the robot. So, okay, so one mention is that these are actually not many robots at the same time, but it's just a single robot with many instances. Yeah. Okay, to summarize, we are focusing on decision making under uncertainty for autonomous machines, and we focus for both on robotics and develop AI methods in, for example, in reinforcement learning and planning under uncertainty, and then we apply the methods on robots. And we are also collaborating with some companies on mobile heavy machines control and other things. Yeah. Thank you.